Dear students, welcome to Probability lecture number 2. In today's lecture, we are going to discuss mutually exclusive events, theorem of total probability, compound events, and theorem of compound probability. And if time permits, we will also go for problems. So let us begin with mutually exclusive events. So last class or last lecture, we discussed about mutually exclusive events. Events are said to be mutually exclusive if the happening of any one of them prevents the happening of all the others. For example, when you throw a die, then if you get 1 point, say, then you will not get the other point, that is 2, 3, 4, 5, 6. So this is what an example of mutually exclusive event is. If you toss a coin, then you get two mutually exclusive cases. One is head or another is tail. You will get either head or tail, but simultaneously they will not occur. Next, let us move on to theorem of total probability. Theorem of total probability says that if there are n mutually exclusive events, capital A1, capital A2, capital A3, capital A suffix small n, whose probabilities are P of A1, P of A2, P of A3, and P of An respectively, then the probability that any one of them will happen is the sum of their separate probabilities. So basically, theorem of total probability deals with OR statement. If there are so many events, then the probability that any one of them will happen is sum of their separate probabilities. So this is your statement, mathematical statement. P of A1 plus A2 plus A3 up to An is P of A1, P of A2, P of A3 plus P of An. Here this is OR statement, you can say. So this is the thing. Next, let us go on. So here, as I already mentioned, A1, A2, P of A1, A2, A3 plus up to An represents probability of occurrence of at least one of the events, A1, A2, An. So this is important, at least one of the events, A1, A2, An. So how to prove this theorem, that is theorem of total probability? So let us consider that there are capital N total number of exhaustive, mutually exclusive, and equally likely cases, out of which M1 number of cases are favorable for A1, M2 number of cases are favorable for A2, and Mn number of cases are favorable for An. So this is the thing. Then the total number of cases favorable for either A1 or A2 or A3 or An is given by M1 plus M2 plus M3 plus ... up to Mn, because when you consider M1 plus M2 plus M3 plus Mn, that is this thing, then it will give you cases which are favorable for event 1, event 2 and event Mn. And the theorem already tells that we have to take the conditions that at least one of the n events occur. So here either event 1, event 2, event 3, all of their cases are included within this M1 plus M2 plus M3 plus Mn that is the happening of either M1, either event 1 or 2 or 3 or Mn, all are included when we take the number of cases favorable for this, either A1 or A2 or A3. Okay, then you will see that the probability of happening of at least one of these events, that is either A1 or A2 up to An, is given by, or it is written as P of A1, A2, A3, An, this. And now, as per definition, probability is number of favorable cases divided by total number of cases. Number of favorable cases for either A1 or A2 or A3 is M1 plus M2 plus M3 plus up to Mn, and total number of cases which we already shown is capital N. So now on expanding this, you will get M1 by N, M2 by N plus dot 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 plus up to Mn by N, which is nothing but P of A1 plus that P of A2 and plus dot dot dot. So this is how, here it is not visible, but it is M1 by N is P of A1, M2 by N is P of probability of A2, and plus our last one will be P of An, this one. Okay, so this is about your theorem of total probability. We have shown that probability of A1 plus A2 plus A3 plus up to An is equal to P of A1, P of A2, P of A3 plus dot 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 up to P of N. Next, we'll go to another theorem known as general additive theorem of probability. General additive theorem of probability is also known as addition law of probability. So what it is? The statement says that the probability that at least, again I repeat, that at least one of the two events occurs is equal to the sum of probabilities of each event minus the probability of both the events occurring simultaneously. So here we have a condition that both the events can occur simultaneously. The previous one was there, but they were mutually exclusive. So here in this particular theorem, general additive theorem, the difference with the previous one is that we are considering two events, not like n events, plus there is a possibility that both the events can occur simultaneously. So probability of at least one of the two events, that is P of A plus B, is P of A plus P of B. So if the events are mutually exclusive, then this condition, that is probability of happening of both of them, will definitely be 0, and it will be P of A plus B will be P of A plus P of B, which will be two event scaling of the above theorem, that you can say that it will be like this. Okay, so then we will move on to the next. So let us try to establish this general additive theorem of probability. To establish this general additive theorem of probability, we will again move to the slide and let the number of cases favorable for both the events happening is n of AB. So n of AB represents the number of cases for happening of the both the two events. Number of cases favorable for capital A only is n of A B bar. Here bar means that B event does not occur. So the symbol is n A B bar. Number of cases favorable for B only is n A bar B. Why A bar B? Because it represents the events favorable for B only, not A. So this is exclusive for B, this one is exclusive for A. So next, number of cases favorable for happening of none of the events. Yes, there is a possibility that none of the event occurs. So in that case, it will be n of A bar B bar. So now if n small n represents total number of cases, then by definition probability of A plus B, that is probability of at least one of the two events, is, here you see that the cases favorable for both the events, that is this, cases favorable for both the events n of AB, cases favorable for A only, cases favorable for B only. So this is the only possibility, that is total favorable cases, that AB bar and A bar B, it includes all, that is it includes all the possibilities of at least one of the two events. So favorable cases by total number of cases. So now probability of A, that is probability of happening of A, is equal to n of AB plus n of AB bar. That is, here A happens together with B, here A happens exclusively without B, divided by total number of cases. Probability of B is simply n of AB. Here B happens with A, and in this case B occurs exclusively, so n A bar B divided by n. And probability of simultaneous occurrence of A and B is number of cases favorable for AB by n. So this probability of A plus B is now done rewritten. Actually, you will see that there is this one, which is your A B n AB by n, that is also here in AB by n. It is just put to as a mathematical adjustment, but as you go you will see that this will give us, this first one gives us P of A, second one gives us P of B, this second one, and this one gives us P of AB. That is, this one, which was written for probability of at least one of the events, now is expressed in terms of P of A plus P of B minus P of AB. That's all, very simple. So by this way you are able to write or prove the addition law of probability. Now, as I already mentioned, that if the events A and B are mutually exclusive, then n of AB is 0, that is, they cannot occur simultaneously, then number of cases favorable for AB is 0, and so P of AB is 0, and probability of occurrence of at least one of the events is simply probability of A or B, which is P of A plus P of B. That can be two event version of the theorem which we proved earlier, that is the theorem of total probability. P of A1 plus A2 is equal to P of A1 plus A2 only. Okay, so this is about general additive theorem of probability. Next, let us discuss about conditional probability. In the last lecture, we discussed conditional probability, and this conditional probability is related with occurrence of one event provided the other event has already happened. So conditional probability P A given B is the probability that event A happens with B has already happened. It is written as P A vertical bar B, which is probability of A given B. Now let us discuss what is called compound event. So it is not composite event, however, it is compound event. So compound event is when two or more simple events occur in connection with each other, then the joint occurrence is called compound event. So for example, when you have a box containing red and green balls, in the first draw you take a green ball, and the second draw you take a red ball. So this type of events can be thought to be the examples of compound event. So theorem of compound probability is also there. What is theorem of compound probability? The probability of occurrence of both the events is equal to the product of absolute probability of one event and the conditional probability of the other. That is, P of AB is equal to P of A multiplied by probability of B given A. So this is your theorem of total probability. The probability of occurrence of both the events is equal to the product of absolute probability of one event and the conditional probability of the other. So it can also be written as P of B multiplied by P of A plus B. So how to prove theorem of compound probability? Here you see that it means probability of A, B, that is your probability of simultaneous occurrence of both the events, and that is the product of P of A and P of B given A, or P of B, P of A given B. To prove this again, we will go to basics. Suppose you have a small number of equally likely small and equally likely cases, and then n of A, n of B, and n of AB, they denote number of cases favorable for the events A, B, and AB respectively. Then probability of B given A can be written as n of AB by n of A. Probability of A given B can be written as n of AB by n of B. Now how this possible? How can you tell that probability of A given B is equal to n of AB by n of B? For this we need to go a little to the another slide, which I am going to show you here. Here you look at this diagram. This diagram, we want to explain that P of AB is equal to n of AB by n of B. That is, number of cases favorable for AB event by number of cases favorable for B. What is probability of A given B? Probability of A given B is such that you have to find probability of A provided B has already occurred. So if you want to find probability of A given B, then you have to find number of cases which is favorable for both the events. This Venn diagram clearly illustrates that number of cases favorable for both the events, this area, this area, this shaded one, and this B. So the number of cases which are favorable for A inside the cases favorable for B. Number of cases which are favorable for A inside the cases which are covered by B only, that is this shaded portion, will give you probability of A given B. So that is why it will be number of cases favorable for happening of both the events A and B by number of cases favorable for B. Fine, so this is that. We'll move on to the previous one. So here probability of A given B is n of AB by n of B. Probability of B given A is n of AB by n of A, and probability of AB is simply number of cases favorable for AB by n, and hence this one P of AB can be rearranged like n of AB by n. N of A is introduced intentionally to convert it into a form, and you will see that n of AB by n of A, this one is probability of B given A, and this one is probability of A. So we have proved that probability of AB is equal to probability of B given A multiplied by probability of A. Likewise, you can prove probability of AB equal to probability of B multiplied by probability of A given B. This one you try yourself, and I hope you will be able to get it. It's not difficult at all. So now this is your theorem of compound probability. Now we can generalize this theorem of compound probability. For the sake of simplicity, we will avoid it. That is, probability of simultaneous occurrence of A1, A2, A3 up to AN is simply product of probability of A1, probability of A2 given A1, probability of A3 given A2, A1, and continuation of that. So we will avoid this for the time being. Again, I would like to tell you one thing, that if A here happens independent of B, then probability of AB will be simply probability of B multiplied by probability of A. If A is independent of, and that A is not dependent on conditionally on B, that is probability of compound event PAB is simply probability of B multiplied by probability of A. Okay, so this is how we'll proceed. Now let us try to see some problems here. One simple problem that I am going to show you is that in your examination they might ask you problems of this category where you are asked to find P of A plus B, P of A, P of B minus P of AB are given to you, and it's very simple. PA will be provided, PB will be provided, and P of A, P of B, the product, and so this is the result is 0. Here P of A was provided as 0.6 in the problem, P of B was 0.2, so the result is 0.8 minus 0.12 by 0.68. Sometimes they will tell you is that find out probability of A plus B, that is at least A or B, and A and B are independent. When they tell you independent, then this product will be 0. Probability of AB will be 0. Next problem which we are going to show you is a card problem, and in this case we have a card is drawn at random from a pack of 52 playing cards. What is the probability that the card is either a king or a queen, either a red card or an ace? So to solve this problem, you will first see that the problem tells you have to find the probability when the card is drawn, whether it is either a king or a queen, either a red card or an ace. So as I told in my previous lecture, you should know the constitution of a pack of cards. So let us go to problem 1. That is, we want to find whether the card drawn is either a king or a queen. So let capital A with the event that a king occurs and V with the event that a queen occurs. So we have to identify the events A and V, and then how many kings are there? There are 4 kings and 4 queens in a pack of 52 cards. Okay, then since you have 4 kings and 4 queens in a pack of 52 cards, therefore the probability of A, that is probability of getting a king, is simply 4 total number of cases, favorable cases, by total number of cases, that is your 52. Then that is queens are also 4 in number, so probability of B will also be 4 by 52. So probability of A plus B, that is either a king or a queen, is probability of A plus probability of B minus probability of AB. Now you might think that why did we include probability of AB? We included probability of AB because there are possibilities of getting a simultaneous occurrence of both these events AB in this problem. So that is why we should consider this, and we should check or verify whether this is possible or not. So here in this case you see that the probability of AB is 0, that is the events A and B are mutually exclusive, that is probability of AB is 0. So probability of AB is 0 because when you get king then you can't get queen or vice versa. So here it simply reduces to probability of A plus B is probability of A plus probability of B, which is 4y52 plus 4y52, 2y13 on simplification. Now if you see the second part of the problem, it tells that either a red card or an ace. So either a red card or an ace. It means that you get a red card as well as an ace. So in a pack there are 26 red cards, 13 and 13, which we discussed last time, and the aces are 4 in number, that is you have 4 suites, each suite has one ace. So there are 26 red cards and 4 aces. Let capital A be the event that a red card occurs and B be the event that one ace occurs. So since there are 26 red cards, probability of A is simply your 26 by 52, and how many aces are there? 4. So probability of B is 4 by 52. Now interestingly, in a pack there are 2 aces of red color also present. There are 2 aces which are red in color. So the result is that probability of A plus B, here you cannot avoid that probability of AB because there are 2 aces of red color. So there is a possibility of getting 2 aces of red color also, that is you will get probability of simultaneous occurrence of red card as well as ace, and so that number is 2. So you have a probability of AB 2 by 52. So you have probability of A plus B is equal to probability of A plus probability of B minus probability of AB, which is 26 by 52, P of A, P of B, and P of AB. Result is that 28 by 52. On simplification it gives you 7 by 13. Okay, so this is one more problem of our probability. So now let us move on to some more problems at the in an examination. One problem was asked. This problem linked with probability is here. We found out the problem. The problem was that find the expected number of heads when n coins are tossed. So when n coins are tossed, then you have to find expected number of heads. You have to find, that is the thing. So if you take a fair coin, definitely the probability of getting head is 1 by 2, and you know probability of simultaneous occurrence of two events is P of AB is equal to P of A and P of B for independent events. If you consider that n coins are tossed simultaneously, then the interesting thing is that they are independent of each other. So you can extend this P of AB equals to P of A, P of B, this theorem to n number of events. So when you extend this, then it will be P of A, B, C like this. So here total probability, required probability for this case is half, 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 half. It will be half to the power n simply. This is the result, is the answer for this. Okay, so this is the year, and again I would like to go up to a problem which we want to conclude with this problem. So now we have a problem here. In a college, 25% of the students, they fail in mathematics, 15% of the students fail in chemistry, and 10% students fail in both. So a student is selected at random, and the question asks that what is the probability that the person failed in mathematics given that he already failed in chemistry. Second, he fails in math or chemistry. So as you see the problem is different. That is, two problems are not the same. One tells that he fails in mathematics. There is a condition given that he fails in chemistry, and he fails in math or chemistry. There is a or statement here. So the solution, we will have to first make the respective probabilities. So 25% students fail in mathematics. Since 25% students fail in mathematics, therefore we consider A to be the event which represents a student fail in maths. B represents the event which a student fails in chemistry. So P of E, as per the question, 25%, that is 25 by 100. P of B, which is 15 by 100, and P of AB, that is student failing in both the subjects chemistry and mathematics together, that is 10 by 100. Now problem 1 tells that probability that he fails in mathematics given that he fails in chemistry. So you have to find probability of A, probability that he fails in mathematics given that he fails in chemistry, that is B means fails in chemistry, this one. So to get this P of A bar B, you know that it is equal to PAB by P of B. So probability of AB, which is 10 by 100, and that one is your 15 by 100. So this is simply giving you the value, that is probability of A given V, that is the student fails in mathematics, given that he fails in chemistry, comes out to be 2 by 3. Second, he fails in maths or chemistry. So when it tells that he fails in math or chemistry, then as we already showed you that you have to go to the or statement. So or statement means P, A or B. So this theorem, which is equal to P of A plus P of B plus P of AB. So in this case, you will see it to be like this, and here you have this P of A, which is 25 by 100, P of B is 15 by 100, P of AB, that is failing in both the subjects, also comes simultaneously. You have to find either failed in A, that is in mathematics, or chemistry. So this is the probability. Here it will come out to be 10 by 3 by using that or. So with this, I would like to conclude today's discussion. So to wind up, let me tell you what we learned today. Today we learned mutually exclusive events, theorem of total probability, compound events, and theorem of compound probability, along with problems. So next class we'll discuss probability distributions.